All right, guys. Welcome back. So I hope I'm audible. So basically, this is an extra session to what we have already completed. Just 1 second. Okay, so basically this is an extra session. So the idea of this session is that we basically didn't have a recap of what we learned in the last session. So I just requested them to have a brief, like 1 to half an hour session uh, on I mean today before your exam commences or before the course ends officially. So and also like we were like if you were present in the last class, we discussed something which is known as the Rayleigh stability equation, which also you have seen multiple times in your sessions on hydrodynamic stability. But I said that although we evaluated the Rayleigh stability equation, which essentially came out to be an eigenvalue problem, I was yet to show you how do we solve an eigenvalue problem. Okay, so this was something that was left to discuss. And the third thing is that if you have any doubts, okay, related to your exams, although like I don't know at this point of time, okay, what would be the pattern of your exam, although it's a computer-based exam. But like if you have any doubts on that, I can forward your doubt to the competent authority, and then I will obviously share the response to your queries on that. So these are the three agendas what this session is actually meant for today. It will be a brief session. It will not last for 2 hours or like 1 hour 45 minutes. It will not last that. It will not be that long. We will try to finish when we are done. And then like if you have any doubts, you can obviously ask me regarding all the sessions that we did. And then uh, on your doubts on examinations and all, I will forward it to the competent authority of the course. Okay. So I hope the goal is clear for today's session. So first of all, before like me trying to tell you like what we will do today, as I already said that yeah we will indeed learn how to solve an eigenvalue problem because the Orr-Sommerfeld equation or the Rayleigh stability equation that you guys saw in the stability analysis, uh, that indeed were an eigenvalue problem, and we must know actually although it is not the they might not be asked in your exam, but uh, it should be at so we should have a path known on how to actually solve an eigenvalue problem. Okay, but before that if you have anything to ask, okay, if you have anything to ask related to, so one thing that we have not covered is the turbulent flow. So I think for the turbulent flow, it is the last part of the week, and I think the lecture notes that you have received and the videos of the lecture that you have seen in the last week is sufficient for you to like answer questions on turbulent flow. And it is just the preliminary concept that you learn for turbulent flow, the various turbulent models like K epsilon, K omega, whatever it is. It's just the start that you learn. So we will not go into the depth of solving problems on turbulent flow, and the series and the theory classes would be sufficient for you to like grasp what was actually the essence of learning turbulence. Okay, so before me trying to show you how essentially we will actually solve an eigenvalue problem, and finally I will do a quick recap of the course on what we actually learned basically in the theory and the interactive sessions. If you have any questions that you seek to be clarified, you can ask me. I will try to address it to the best of my abilities, or I will always try to forward it to the competent authority if I am not able to answer your queries. So I'll wait here. So I'll give you ample time today. I'll wait here for maybe 5 to 10 minutes. If you have anything to discuss, you can let me know on it. And I'll also wait for a couple of times so that the like one or two more people can also join. So I'll wait here maybe for a couple of minutes. So there is a question, is there negative marks for wrong answers in the exam? So yeah, so actually, Jose, the thing is the exam pattern that so the exam pattern that the NPTEL people and the course coordinators suggest, it changes every time. Okay, although it will be a computer based exam, the concise like information on that is still not available to me, but but like I will forward your query to the authority, and like if I receive an answer, I'll post it in the discussion forum. Okay, so I'll just write down your queries. Okay, so your query is that so your first query is negative marking in the exams, in the exam. Okay, this is the first query, but so far as I know, okay, so far as I know, see, I'm not sure about this, but like till last year, I don't think so. There was negative mark in the computer-based exam that happened for this course. Okay, so I do not think so. I think it will be more or less similar to the assignment questions that you did. So I don't. So you don't have a negative mark in the assignment question, right? So am I right? So did you get my point? So I'm just asking that you don't have a negative mark in the assignments, right? So I hope you don't have there. So I believe the examination pattern will be similar to the ones that you see as a part of your assignment, okay, which is more or less related to the theory classes and few of the sessions that we did. Okay, it will be more or less similar to that, and I don't think so there will be a negative mark in this year's pattern as well. But to this end, I am saying that I'm not so I didn't receive the pattern of the paper yet. So like I will like I cannot comment surely on that, but I will let you know if at all like I get this information. Okay. So is there also anything else? First one is so I think one of the students in one of the like sessions asked me about the ambiguity in some problems of specifically in assignment 5 and I think assignment 7. So I have conveyed the like so I've conveyed them to the TA who makes the questions and the instructor. So if so, I didn't check that question by myself, but if at all the question was wrong, you will be awarded marks in the assignment and you will be re-examined. And if the question is right, but there is some, so I hope the TA and the authority and the competent authority have answered your doubts in the assignment thing that I think some of you have asked in maybe 3 4 sessions back on I think assignment 5. And I think there was one question on boundary layer where there was one ambiguity with one option that option. So it was the I think if I correctly remember, it was related to the boundary layer thickness and the velocity profile. It was something like that. So I have forwarded that question and I have said to myself that the correct answer should be the other one instead of the given answer. But they have not revert back to me as of now. I will again remind them, and if that was or if that question was wrong, then you will be given your duly like so whatever marks you will get, you will be like added to that assignment. Okay, so this was something related to the assignments. Okay, so anything else? If you want to ask, you can let me know, or you can type in the chat, and or like and then we will just okay, how many questions will be there in the exam? Again, that so that is a subjective question, I would say. Okay, so as I said, the pattern does not remain the same always. Okay, it changes basically. So I can't tell you how many will be the exact number of questions, but so the first query I can sort it out, but I don't know if they will answer the second query or not. But anyway, I'll just write it down. So you are asking me how many number of questions. So for that, can you tell me like one thing that how long is the examination? Can you tell me? I didn't check it out. So did they tell you that this is the time period of the examination? So how long is it? So you were asking how many number of questions tentatively. So how long is your examination? Do you know that? All right. I don't know. I don't know if you can hear me or not, but it's okay. So how many questions? I don't know that they will answer this because this is a subjective question. I mean, this is a subjective point actually, that this always varies on the pattern of the examination day sets. Okay, so yeah, first point I can try to figure it out, but second point I really don't know. Like, uh, I'm not sure about that. So that depends on how long the examination is. Okay, but one thing is that the questions will be more or less similar to the ones that you solve in your assignment. It is not that they will give a different questions out of nowhere and you have not seen that. It is not like that. It will be similar to the ones that you solve as a part of your assignment. That's it. That I can like say to you. Okay. All right. So okay. So if you don't have any other questions, uh, we will proceed with a final thing before like ending the session officially. So in the last class, what we saw is we saw basically how to like how do we get the Rayleigh stability equation. So we solved basically. So if you remember, what we did is we started off with not here. I think this here. So we started off by applying something known as the squares theorem. Okay, and we applied squares theorem to eventually find out that the 2D disturbances. So we applied squares theorem to eventually find out that the 2D disturbances are stronger than their 3D counterparts. So this is known as the squares theorem basically. And so what we did is when we applied squares theorem, our three-dimensional equation for disturbances, which are ODEs of course, after like decomposing the variables into the normal mode analysis, our three-dimensional equation reduced to a two-dimensional equation, and we use something which is known as the stream function approach to eliminate pressure and then eventually find out an ODE, which is known as the Rayleigh stability equation. So this is precisely the Rayleigh stability equation, where U denotes the base flow, C is our so U is, so as you know, this base flow information is known to us. However, this C happens to be the eigenvalue of the problem for which we are trying to solve for, and this phi is known as the eigenfunction corresponding to the eigenvalue. Okay, and this alpha that you see here, these are the wave numbers precisely. And since we are now interested in only the x and z direction because we are in the 2D domain, we will just consider the wave number in the x direction, and hence we just end up getting alpha here, and the beta, which was the wave number in the 3D space in the y direction, gets omitted in this context. Okay, so as you know, this equation that we saw, that we essentially derived in the last class, is the infamous Rayleigh stability equation. Okay, which is an ODE, as you can see. Okay, this is an ODE. It's a second order equation, and of course it is homogeneous. Okay, it's homogeneous because the solution phi equal to 0. Okay, so this phi equal to 0 satisfy this equation. Okay, so that's why it's a homogeneous equation. It's second order because of this term, which is d2 phi by dz square. And yeah, so as you can see, this equation also involve finding out C. Okay, which means as a part of our solution we need to find out the eigenvalue and the eigenfunction phi. Okay, so now the natural question arises that how do we solve this equation? Okay, we know that we get this equation by doing those stability analysis, that linear stability analysis steps that we did. Okay, that writing the governing equations for perturbations, invoke the normal mode analysis, applied squares theorem, then eliminate pressure by using stream function to get the Rayleigh stability equation. But still the question arises that how do we solve such kind of equation? Which is basically an eigenvalue problem. Okay, so that is something that we will discuss today, and this is precisely the topic of discussion for today. So the idea is, I'm just writing that solving and eigenvalue problem. Okay, so I'll now show you that once we encounter an eigenvalue like problem, how do you go about to find the solution? Okay, so in this context, I would basically tell you that there are two approaches. If the governing equation is simple enough, we can resort to something which is known as the analytical approach. So this is fairly straightforward, and you will come to see why I told this. And if it is not straight, if it is not analytically tractable, for instance, the Rayleigh stability equation, you cannot solve that analytically. Okay, and for that you need to go for numerical approach. Okay, so we will look briefly by following a prototypical example, okay, which is not so complex like the Rayleigh stability equation, but it resembles the nature of like what an eigenvalue problem essentially is. Okay, so one is basically the analytical approach and the second is the numerical approach. Okay, so like let's go first to the analytical one. So let's say I am solving a, a differential equation which is of this type. Okay, it is d2u by dx square plus c square u of x equal to 0. And since it's a second order, it must have two boundary conditions. So I say that my domain is from x equal to 0 to 1. So u at x equal to 0 is 0 and u at x equal to 1, okay, is also 0. And I tell you that this problem, so can you tell me if this problem is an eigenvalue problem or not? So what makes you feel that this problem is an eigenvalue problem, if at all it is an eigenvalue problem? Okay, so this is something that we already discussed in last class. So can you give me the hint like why this problem is an eigenvalue problem? So this problem is little bit similar. So although it is not that complex, it is similar to your Rayleigh stability equation or your Orr-Sommerfeld equation. Okay, the only thing is that, so here we have just a second derivative in u and a second derivative and just u and multiplied by some c square. Your Rayleigh stability equation was similar, but we have some extra terms. For instance, so for instance, if I just add this term within that equation, it becomes it becomes the prototypical Rayleigh stability equation. So the backdrop is that I have considered a simpler equation just to show you the like methodology. You can apply the same for this equation as well, how to basically solve this. Okay, but before that, my question is, what makes you think that this equation is essentially a eigenvalue problem? Can you like give some thought on that? All right, so I'll give you the hint. So I say that just like let's say we look into the Rayleigh stability equation, which was basically something like this, where if you remember, this phi was your eigenfunction and this c is your eigenvalue. This u is already known to us. Okay, this is just a known function that we are just taking care of, because this base flow, this u as a function of z, which is basically the base flow that we considered when we do the stability analysis of viscous or inviscid parallel flows. This base flow information is always known to us. Okay, so this means this is known to us and this is also known to us. The only thing, and of course the wave number, these are also a known quantity. We don't need to solve for alpha, where this alpha is basically any generic wave number that we are considering. Okay, so this means what we need to do is we need to find out the eigenvalue c and the corresponding eigenfunction, which is phi. This is typically known as the eigenvalue eigenfunction pair. Okay, this is something that we need to find out. So in this equation, as you can see, this is essentially a homogeneous equation. Okay, and I said that when we looked into the boundary conditions of the Rayleigh stability equation, the boundary conditions are also homogeneous. And I stress that whenever I encounter a equation which is homogeneous, just like this, because when ux becomes equals to 0, this goes to 0 and this also goes to 0, which means the governing equation is homogeneous and the boundary condition of u is also homogeneous. So this homogeneous set of equation along with the homogeneous boundary condition is a perfect recipe for an eigenvalue problem. Okay, so I'll just write that since the governing differential equation is homogeneous and the boundary conditions are also homogeneous, this is an eigenvalue problem. All right. So the first step is to acknowledge that this is an eigenvalue problem, and we have rightly done that. So, so when I say that my governing equation is homogeneous, I mean that u of x equal to 0 is a trivial solution. Okay, that is basically something that we all know, that whenever we encounter a homogeneous equation, we always have a trivial solution, u of x equal to 0. The crux is that we are not interested in looking trivial solution, we are interested in looking solutions where u of x is not equal to 0, and that basically is an eigenvalue problem. Okay, so now what we will do is, if we want to seek the solution which is not a trivial solution, we will basically have to solve this governing equation subjected to these two boundary conditions. Okay, so if we see this equation, I have taken it to be a simple equation, and that's why we can solve this analytically. I will show you how do we in general solve such kind of equation numerically also in today's class, but let's try to first see an analytical solution to this equation. So can you tell me how do we solve this equation subjected to these two boundary conditions? What's the solution of this equation? Can you tell me? See, this is fairly straightforward. See, this is an ODE, okay, which is an ordinary differential equation of second order. So I guess you guys you guys are well versed with all those mathematical tricks now. So what we do is we will take u of x as some e power lambda x. Okay, so this is a traditional way of solving these kind of second order ODEs. Okay, so if u of x is just some e power lambda x, we will evaluate what is du by dx. This becomes lambda times e power lambda x, and d2u by dx2, this becomes, so what does it become? It becomes lambda square e power lambda x. Okay, so now once we evaluate all these things, what we do is we substitute this in the governing equation. Okay, and when we substitute this, what we get is we get lambda square e power lambda x, that comes from the term of the second derivative, plus I have c square times u of x, so it becomes c square times u of x is e power lambda x, and then it becomes equals to 0. And since we are not interested in trivial solution, e power lambda x cannot be equal to 0, because the otherwise becomes a trivial solution, and we are not interested in that, which means I end up getting lambda square plus c square equals to 0, which means I end up getting lambda square is equal to minus of c square, which means I get lambda to be equal to plus and minus of I times c, where your I is nothing but square root of minus 1. Okay, so these are the roots of, so this equation is essentially known as a characteristic equation, and these are the roots of the characteristic equation. Okay, so if these are the roots, then my solution of u of x basically is something like this. Okay, so my solution for u of x is some a cos cx. Okay, this is, I'll show you a simple step. So the first step, the solution essentially come out to be some, let's say a, I would say like, let's say some a. So the solution is of this form. Okay, since I considered u of x to be some e power lambda x, and I know my lambda is plus and minus of c, so, and I have two values of lambda which are mutually independent. This means now I will have two solutions of the form some a1 e power lambda 1, and lambda 1 I will write it as plus icx, plus a2 e power minus icx. Okay, I hope you are clear with this. I think you have done many a times in your maths, and also in these courses where you have frequently encountered this sort of solution to the governing equation. Okay, now what I will do is you can always write e power I theta as some cos theta plus I times sine theta, which means you can write this equation as some new constant, let's say a1 bar cos cx plus b1 bar sine cx. Okay, you can try it out, just do the expansion, and just you can try it out that your equation can also be written as in this form. Okay, so that's the solution of the equation that we are trying to find out. All right, so now we are left with calculating this a1 bar and b1 bar, for which we will use the boundary condition. Remember, this c is also a part of the solution that we need to evaluate, because c was our eigenvalue. Okay, so let's use the first boundary condition for that. So if we use the boundary conditions that we have, so what does we have? Okay, the first condition says that u at x equal to 0 is 0, which means I have a1 bar, this comes out to be 0. Okay, and the second boundary condition is what? So this is our first unknown that we get from the first boundary condition. And if I use the second boundary condition, it says that u at x equal to 1, this is also 0. Okay, which means what? Which means that b1 bar times sine c, and this is equal to 0. Okay, now here is the thing. I have one option which says that b1 bar can be equal to 0, but this is not possible. See, if this is possible, that means, see, a1 bar is always equal to 0, and if I put b1 bar to be also equal to 0, this means what? This means that I am just writing u of x is just equal to 0 is the solution, which again is a trivial solution that we are not trying to seek for. Okay, we are not interested in trivial solution, and that's why b1 bar cannot be equal to 0, which now means that sine c has to be equals to 0. Okay, and this means that your c should be equal to n pi. Okay, where your n is plus and minus of 1, plus and minus of 2, and plus and minus of 3, and so on. Alright, which means I have now completely evaluated u of x, which is of the form, okay, some b n bar sine cx, and c is n pi, so it becomes sine n pi x, where your n is plus and minus of 1, plus and minus of 2, and so on and so forth. So in this context, we have successfully determined what is the eigenvalue of our problem. Okay, and the corresponding eigenfunction u of x. Now remember that is b and sir, these are also an unknowns. Okay, so in order to solve this eigenvalue problem, we also need another set of equations to completely determine the eigenfunction. But since our in most of the eigenvalue problem, our interest is to calculate the eigenvalue and not the eigenfunction. So in this context, the two boundary condition of u is sufficient for us to know what will be the eigenvalue. Okay, so that's the idea that I want to convey. So if you have any questions on this, you can let me know, and we are free to discuss. Okay, so what I mean to say is that for completely determining the eigen function u of x, okay, we need another condition on ux. But the two conditions, okay, the two conditions, that is ux at 0 equal to 0 and ux at 1 equal to 1, is sufficient for us to know what will be the eigenvalue of our problem. Okay. All right. So this looks pretty simple. Okay. Why is it simple? Because the governing equation was such that we have an analytical approach to this governing equation. However, often in life, and of course in this course, you will not encounter such simpler and such simple governing equation. And for instance, if you want to solve the Rayleigh stability equation or the Over-Sommerfeld equation, you cannot solve it analytically. You need to go for numerical solutions. Okay, and that's why I will now show you the second approach, which is a more generic approach, which is the numerical approach. Okay, so I'll show you the second approach, which is basically the B, and this is nothing but I'll say it's the numerical approach. All right. What I mean by this numerical approach is that we seek for numerical solution by discretizing the governing equations. Okay. So I hope you have some basic knowledge. Oops, I think there is a lag in my screen. I don't know. Okay, this come now. Okay. So what I mean to say is that, I mean, in numerical approach, we follow something which is known as discretization. Okay, and there are multiple ways of discretizing a governing equation. For instance, there is something which is known as finite difference method. There is something which is known as finite volume method, or there is something which is known as finite element method. Finite difference method is the most simpler method. Okay, and this is yet if even if it is simpler, it's very powerful. And if we are mostly dealing with 1D systems, we generally resort to finite difference method. Okay, so what we will do is we will the same problem that we solve analytically, we will now try to solve it numerically. Okay, such that I can give you a flavor of how basically do we solve eigenvalue problems in a generic way in using the numerical approach. Okay, so what we'll do is we will use the same equation, okay, which is basically this. So we will use the same our same governing equation, which was d2u by dx2 plus what is it, I think the c square times u of x, and this is equals to 0, and I know that u at x equal to 0 is 0, that is from the boundary condition, and u at x equal to 1, this is also equal to 0. So I have this equation. Now I will use a numerical based discretization technique, and I will use finite difference method, okay, to basically discretize this equation. The idea of discretizing a governing differential equation is to convert the differential equation into a systems of algebraic equation. Okay, and once we convert it into a system of algebraic equation, we basically follow something which is known as the matrix multiplication, which basically gives us a coefficient matrix times the the variable matrix, and this becomes equal to the constant matrix. Okay, so we follow something like that to essentially calculate what will be the unknowns that we seek to calculate. Okay, so this is something that we are going to do. So what we will do is we will use finite difference method, okay, to solve this eigen value problem. Okay, and let me show you how. And I don't know like of which background you are, that you are familiar with these techniques, this discretization technique or not. So what I will do is I will assume that like you are not familiar with this, and I will try to show you this from very scratch. Okay, but so if you have gone through any courses of CFD, then this is the first thing they teach you as a part of discretizing governing equation. Okay, so what we will do is, what basically we do in a finite volume method is that, so we know that our domain in X, okay, what we know is that we know that our domain in X, okay, varies from 0 to 1, which means this point is basically our X equals to 0, and this point is basically our X equal to 1. So what we do in discretization technique is that we divide this domain, okay, we divide this domain into very small points, okay, something like this. See, the idea is to convert the differential equation into an algebraic equation, into a system of algebraic equation, and for that we divide this domain into these small points. So the last points, so these points, okay, this and this, these points are known as boundary nodes. Okay, these points are known as boundary nodes, and the signature of the boundary conditions are embedded in these boundary nodes. Okay, so I will name these nodes as something like this. So the first node I will name it as 1, the second node I will name it as 2, the third node 3, and like this I will name a generic node here as I will name a generic node here as I minus 1, and this generic node I will name it as I plus 1. The last node will be our node n, and this penultimate node will be n minus 1, and so on and so forth. Now, a natural question that might arise to you is that how many nodes or how many points do we need to build in here, or do we need to like put in here? The answer to this question is that the more the number of points you put, okay, the more accurate your solution will be. And after a certain let's say after a certain number of points that you put in, for instance, if you put in, let's say 1,000 points, and if you add 100 more points, let's say 1,100 points, 1,000 plus 100 points, your solution will be independent of the number of points that you put in. Which means, let's say if you put 10 points, okay, in between these nodes, I mean, if you just choose 10 nodes in between this grid, or in between the values from x equal to 0 and 1, okay, your solution will not be accurate. But if you, let's say, choose this n to be equal to 1,000, okay, that means if you just pop in 1,000 points here like this, okay, then if you then put in, okay, let's say if I put in 10,000 points, will my solution will be more accurate? That's not the case. Okay, after a certain value of the number of points that you put in, your solution become independent of the number of points that you are going to put in after that value. This is something which is known as grid independence. Okay, so what I am telling is that after certain value of n, your solution will be independent of the number of grid points. And this thing, in technical terms, it is known as grid independence. Okay. All right. So now at least we know that how do we choose these points, and is there a limit to the number of points that we put in here. Okay. Now once we are done dividing this domain into this number of points, what do is we try to write down the governing equation at any generic point, let's say I. Okay. So what I mean to say is that I try to evaluate this d2u by dx2 at the ith point, which is any generic point in between the boundary nodes. Okay, what we will do at the boundary nodes is something that we will see later on, but let's now write the governing equation at any ith point which is between the boundary nodes. Okay, so if we use finite difference method, okay, this term d2u by dx2 at the ith node becomes something like this, and I hope you are familiar with it, but still I'm just writing it for the sake of for the sake of completeness here. Okay, so d2u by dx2 becomes u of I plus 1 minus 2u of I plus u of I minus 1 divided by delta x squared, where this delta x is essentially the distance between the 2 points. Okay, and this is something that we choose from ourselves. All right. Again, I think there is some lag in my screen. I hope this, I don't know. Oops, okay. So now I think this is working. Okay, so what I mean is that the delta x is essentially the distance between any two successive points. Okay, any 2 points that we are considering, and this delta x is something that we choose from our hand. Okay, so it's like after a certain value of delta x, okay, you cannot choose this delta x, let's say, to be a very big value, then your solution will be not grid independence. But if you choose delta x to be sufficiently small, and after that sufficiently small value, if you go on decreasing the value of delta x, your solution will be independent of the delta x that you choose, and that, as I said, is known as grid independence. Okay. All right. So in finite difference method, what we do is we write the second derivative as something like this. Okay. So this means the second derivative at any ith node can be written as its value in the I plus 1th node, the ith node, and the I minus 1th node, divided by this term delta x squared. Okay. So if you ask me how do you get this, it is simply obtained by using Taylor series expansion. That's it. If you just use Taylor series expansion, okay, at a node I, and then you just expand it to its neighboring node, you will simply get this form of things that you write here. Okay, you can refer to any book, any standard book on finite difference method on how do you basically write this from this, but it is fairly straightforward. Okay. All right. Similarly, okay. Similarly, but remember that this is not exactly equal. So what I'm saying is that this is not exactly equal to this, but there is a correction which is of the order of delta x squared. Okay, so the other terms would be at least of the order of delta x squared or more, which means that if my delta x squared is very small, then I can neglect this term. Okay, then I can neglect the corrections which will be of the order of, correction means the error, okay, which will be of the order of delta x squared. So I can just neglect it and I can say this to be equals to 0, or it's better to write, I'll just neglect the corrections to this term, which means I can write d2u by dx2, okay, at the ith node to be approximately equal to this quantity u of I plus 1 minus 2 times of u of I plus u of I minus 1 divided by delta x squared. Okay, so this process, okay, this process of actually writing the derivative into its values at the ith node, the node at the, like, at the point before the ith node and the point after the ith node, is known as discretization. As I have said, this is known as discretization of, so this is known as discretization, okay, at the ith node, or sometimes people call it as grid points in the language of CFD. Okay. Alright, so once we know how this second derivative would look like, what we will do is we will substitute this into this governing equation. Okay, when we do that, what we will get is something like this. So we will get what? We will substitute that and it becomes u of I plus 1 minus 2 times of u of I plus u of I minus 1 divided by delta x square, okay, plus c square. This u will be just u of I, okay, and this thus becomes c square ui, okay, this is equals to 0. So if I just rearrange these equations, okay, if I just simplify or rearrange this equation, I end up getting u of I plus 1 minus 2 times of u of I plus u of I minus 1 plus c square delta x square u of I, and this is equals to 0. And if I just put the other terms that side, it will become u of I plus 1 minus 2 times of u of I plus u of I minus 1, and this is equal to minus c square delta x square u of I. So this is something that you need to pay attention to. See, what did he do? So just by using this discretization, we have essentially converted the ODE in U into an algebraic equation. Okay, because this, so all we need to know is the value of U at each and every node. Okay, because these nodes, see, this ith node varies from what? It varies from 1 to n. Okay, so if I know the number of nodes, I essentially try to solve these algebraic equation at each and every node. Okay, because this c square and delta x square is something that is independent of the nodes that we are taking care of. Okay, all right. Okay, now what we did is we discretized this equation for any generic node between the boundary nodes. Okay, now the next question comes is what do we do at the boundary nodes? Okay, is something that we need to understand. So let's now consider the boundary nodes. Okay, so let's say I am now considering at x equal to 0, okay, which means I am now focusing at n equal to 1. Okay, what do we have? So we have that u at x equal to 0 is 0. That is from the boundary condition. Okay, so what I will do is, since this is, so this u at x equal to 0 means we are evaluating this at the node 1, I can write it as just u1 at x equal to 0 is 0. And what I will do is I will multiply this equation in the left hand and right hand side with 1 minus c square delta x square. And why we are doing this is something that I'll just let you know. Okay, so this becomes, so this becomes 1 minus c square delta x square u1, and this becomes 0 into 1 plus, so it's not minus, it is plus 1 plus c square delta x square. Okay, So since 0 into this term will just end up getting 0, which means I end up getting 1 plus c square delta x square times u1, and this is equals to 0. So remember, this we are doing at the boundary nodes. Okay, this is we are doing at the left boundary. Okay, just be aware of that. And then what I will do is I will just simplify this as u1 plus c square delta x square u1 is equal to 0, where this 1 subscript denotes the value of u at the left node, which is n equal to 1. Okay, because I'm considering about this node. Okay, I'm just considering about this point that I'm saying. So this point, as I said, this point is basically n equal to 1. This is n equal to 2, this is n equal to 3, and so on and so forth. Okay. See, this equation, this is valid for all the nodes except the node at n equal to 1 and the node at n equal to n. Why this is so? Because see, in this equation, I have something which is known as u of I minus 1. Now, when I apply this equation at the 1 at node, okay, I don't have something which is known as I minus 1 because I don't have 1 minus 1, right? I don't, so it simply does not exist, which means the discretized equation is essentially valid for 2 to this point, which is n minus 1. For the 1 at and the n at node, we will use the boundary condition, and that is something that we have all that we are doing currently. Okay. So for the 1 at node, this basically comes out like this, and I can write u1 as simply minus c square times delta x squared u1. Okay. All right. Okay. Similarly, for the right boundary, for the right boundary, that is at x equal to 1 or n equals to at n, okay, I have un equals to 0. And using the same exercise that we did here, that we basically did here, you can simply show that un is basically minus c square delta x square times of un. Okay. And I'll let you know why we basically did this. Although we know that at the boundary nodes u is basically 0, why did we just convert it into something like this? Okay. This is typically because this is typically because the so you just need to be a little bit cautious about the equations, about the discretized equations that we obtained. Okay, so this is the first equations that was basically valid from 2 to n minus 1. This is the second equation that was the left boundary node, and this is the third equation that is the right boundary node. Okay, in these equations, okay, if I want to represent now this equation 1, equation 2 and equation 3 into a matrix form, I can say that the final discretized form, okay, the final discretized form is of the form something like this. Some matrix A into matrix U is as some lambda times U. Okay, where U is something that we are trying to find out. So if you remember, if you remember, this is exactly what an eigenvalue problem look like, because if there is an eigenvalue lambda, it always satisfies ax equal to lambda x. That is something that we have learned many times in the vector algebra courses. Okay, and what we did is we are all trying to map the equations, for instance this equation or this equation into this form. Okay, as you can see, the right hand side is always similar. Okay, see, it is minus c square delta x square ui, this is minus c square delta x square u1, and this is minus c square delta x square un, which means this lambda, rest assured, this lambda will always be equal to minus c square delta x square. Okay, which means that our eigenvalue that we are trying to find out, c, is something of this form. So c square would become minus lambda by delta x squared. Okay, and c is basically equal to square root of minus lambda by delta x squared. Okay, so this is actually the eigenvalue c that we are trying to find out. It is the same C which is basically n pi when we solve it analytically, which is basically this. But this is something that we are doing it numerically, and that's why it seemingly becomes a little bit complicated. Although it does, although after some practice, okay, of this finite difference method, it will not become complicated to you at all. Okay, so I hope this is clear. So now I know that this lambda is of the form this, okay, and this means if I know lambda, so if I know this lambda, this means I can know the eigenvalue C. Now, how do we know lambda? So if you recall that any eigenvalue problem is of the form some ax, some matrix A into vector x equal to lambda times that vector x, where this lambda is essentially the eigenvalue of this coefficient matrix A, which means this lambda that you write here or that you see here is nothing but the eigenvalues, okay, of this matrix A. Okay, and if this lambda is known, then I can easily find out C, which is actually the eigenvalue of our problem, by using this relation. Okay, so this is the idea. Now, the thing is, how do we know what will be the eigenvalues of this matrix A? Can you give me a hint here? How do we know the eigenvalues of this matrix A? See, this matrix A is something that should be known to us. Then only you can find out the eigenvalues of A. Okay. And this is something that you will see when you have a closer look into these equations. See, the information of A is somehow hidden in these things. Okay, it is hidden in these things. See, if you closely look into this form, into this form and this form, then that A matrix, which is basically the coefficient matrix, is essentially the coefficients of these terms, right? It is basically this coefficient, which means if I want to represent equation 1, equation 3 and equation 2 into this form, it is simply nothing but writing something like this. Okay, so my A matrix would be something like this. It is 1, it should be 1 0 0 up to how much grid points that you take, and this would be 0. The second point would be 1, this would be minus 2 and this would be 1, and I'll show you why this is the case, and the rest all everything is 0. So the diagonal terms are something like this. It will be minus 2, it will be minus 2, and this will continue up to 1. Okay, the off diagonal, this term would be 1, and this term would be again minus 2, this term would be 1, and this term would be 1. So this is the diagonal term. Okay, so this term is basically the diagonal term of the of the matrix A. Okay, and this term that you see here, this is the off diagonal term of the matrix. Okay, and this is the leading diagonal, and these are the two off diagonal terms. That's what I am trying to say here. Okay, and this A matrix is now multiplied with this is u1, this is u2, and this goes up to un. Okay, and then I have the on the right hand side, as you know, I have just lambda times u, which is, so this becomes lambda times of u1 u2 up to un basically. Okay, now if you are not clear how did I write A times u as this, okay, I will show you how. See, if I write the first equation, that means I am multiplying this with this, and rest everything is 0, which means I am just getting u1 1 times u1 equal to lambda times u1. Okay, and this is exactly what we are essentially getting, because this becomes u1 and lambda is minus c square delta x square times u1. Okay, this is something that when I do the multiplication of this with this to get basically this. Okay, and this is exactly the boundary condition that we wrote here. If you just look back to your notes, this is exactly the boundary condition that we wrote here. Similarly, if you do this exercise for this nth node, okay, sorry, this this should be 0 actually. This is not 1, this should be 0. Because for the nth node, we just have un, and this, and un becomes just equal to lambda times un. So this has to be 0. Okay, sorry for that. If you now do this, let's say we are now doing this for, let's say we are doing this for the second node. Okay, let's say we are doing this for the second node. What do we get? We get, so this is for the first node. Okay. So if I now do this for the second node, what we get, so what do we get? We get this 1 multiplied with u1. Okay, I have 1 times u1 minus it is 2 multiplied with u2, so it becomes 2 times u2. Okay, plus if you do that 1 multiplied with u3, because there is this 1 here, this get multiplied with this u3. Okay, then this becomes u3, and this becomes equal to lambda times of u2. Okay, and this is exactly the discretized equation that we wrote here. Okay, this is exactly the discretized equation. Just look back to your notes, and this is exactly what we are writing here. See this. If I write this for I equal to 2, this becomes u3 minus 2 times of u2 plus u1 equal to minus c square delta x square times u2. And this is something that we get when I apply this for the second node. If you do this for all the nodes from 2 to n minus 1, you are bound to get such type of equation. Okay, and that means that the writing this matrix is essentially correct because it satisfies this condition, it satisfies this condition, it satisfies this condition, and it satisfies also this condition which is valid from the 2 to n minus 1 in node. Okay, which means now if we, so this is our A matrix. Okay, this is now our A matrix. So now if I can find the eigenvalue of this matrix, okay, then if I can now find the eigenvalue of this matrix, that means I have determined this lambda, because lambda is nothing but the eigenvalue of A according to the definition of eigenvalues. Okay, and then if lambda is known for each and every values of lambda, I will get the value of C. And you can verify that numerically this value of C would be very close to n pi. Okay, which is basically our analytical solution. And this is something that you can do as a part of your exercise at home, and you can of course try it out. Okay, so so now the question is, how do you find the eigenvalue of this matrix? Because because this matrix is a very large matrix, right? If you take 1000 grid points, this matrix would be a 1000 cross 1000 matrix. Okay, so there is a very nice command in MATLAB. You don't need to solve the system of equations to, or you don't need to do that A minus lambda ka determinant equal to 0. You don't need to do that because by hand it is impossible to do. So there is a very nice command in MATLAB which is known as Eig. So if you just put in the value of A, matrix as something like this in MATLAB and just type Eig of A, this will give you all the n eigenvalues of A. Okay, this will give you all the n eigenvalues of A. This means you know all the lambda n's. Okay, you just know all the lambda n's from here, and once you know all the lambdas, you can find out all the c's from this exercise. And these c's would be equal to n times pi, and you can compare that from your analytical solution. So I hope so. If you are learning this for the first time, it might seem to you that this is completely new, but this is a very famous and a very useful technique to solve equations numerically, not just eigenvalue problems, but if you encounter certain differential equations which are not possible to solve analytically or by using analytical tools, that numerical discretization is very powerful. Okay, and it just boils down to just solving this system of equations. Okay, so this is the case. Okay, this is the case that I want to convey here. All right. If you have any questions, doubts, you can ask me. By the way, this matrix from its nature has got a special name. Okay, and this matrix is known as a tridiagonal matrix. So the idea is that if you are having a second order discretization, which means if you are having terms like d2u by dx2, you are bound to get a tridiagonal matrix precisely because of the fact that when you discretize at any generic ith node, you have ui, you have ui minus 1, and you have ui plus 1. Okay, so that's the idea why you end up getting a tridiagonal matrix basically. If you have terms like, let's say, d4u by dx4, then instead of getting a tridiagonal matrix, you get a pentadiagonal matrix. The reason behind is that if you discretize fourth order, so if you do fourth order discretization, you get terms like u of I minus 2, u of I minus 1, u of I plus 1, I plus 2, and so on. So you have five, basically you have five diagonals over there. And that's why when you do fourth order discretization, you get a pentadiagonal matrix. So naturally, a fourth order discretization is computationally more expensive than than a second order discretization, simply because of the fact that in second order discretization, all are, you just get a tridiagonal matrix. The meaning of tridiagonal matrix is that all other quantities except the main diagonal, the leading diagonal, and the lagging diagonals are all zeros, where you can see from here. Okay, these quantities just are just odd zeros. Okay, and that's why this is known as a tridiagonal matrix. Okay, so that's the idea. There is also a very famous algorithm for solving tridiagonal matrix, which is known as a tridiagonal matrix algorithm, which is known as TDMA. It's a means of solving tridiagonal matrix, but you don't need to learn all those things at this point of time, which, because this is beyond the realm of this course and the things that you are learning. Okay, so with this, if you have any doubts, you can ask me. But this is something that I want to convey through this exercise that we currently did. Okay. All right. If you don't have any doubts, so this is what ends today's session. I will not take any long for like discussing any new topics. Okay. I think this is sufficient for you to like cover up. So I think we have more or less covered up everything that we have discussed, or the theory classes have discussed. Of course, it is not possible to cover each and every topics of the theory classes, typically because like we just get to meet only once a week. So like the idea of the interaction session is just to be some interactions, or just to give some knowledge which might be of your use in this course, which were not touched that thoroughly in the theory classes. So this is how this session goes. So I hope you find the session useful. We will do a quick recap of what we learned, and then we will just end this session. And I'll try to put forward your queries today itself. And I'll post it in the discussion forum once like they are sorted from the other end. Okay, so we will just do a quick recap. So what we did in the first class is we started off with something which is known as learning the fundamentals of fluid mechanics. So we learned something which is known as the Reynolds transport theorem. Okay, we learned something which is known as the stream functions. Okay, and using the stream function basically to solve simple problems. Okay, and then using RTT to find out forces, to use RTT to find out the unknown velocity by using mass balance, and so on and so forth. Okay, in the second session, we solved the Navier-Stokes equation for 1D flows, which are basically like steady, and it was one dimensional. It was simple like flows that we saw. For instance, we solved the Couette flow problem, the Eigen problem, and the plane possible problem. Okay, we solved something like this. We solved the problem which involves like the Taylor-Couette flow, which means that there are two cylinders, or there are two spheres that were rotating with some given angular velocities, and we were asked to find out the flow profile in that things. In the third week, we looked into something which is known as the Hagen-Poiseuille flow, okay, which involves flow through pipes, and we solved some problems related to that. In the fourth week, we added a bit more complexity into our analysis. What we did is we solved some transient problem. For instance, we solved the problem of like oscillating plate flows and something like this. Okay, so for instance, what would happen when there's a plate that is suddenly set into motion, which is the Stokes first problem, or like what happens when there's a plate which starts oscillating after time t equal to 0 plus. And also we looked into a problem which is known as an oscillating pressure gradient problem in a channel, which means it was the same problem as that of a Hagen-Poiseuille flow. Only the difference is that the pressure gradient, instead of it being a constant, it becomes a function of time. And in fact, it becomes a cosine function of time, having some frequency of omega inverse. Okay, we solved that problem, and we saw that the answers essentially came out to be in terms of the Bessel function, as we saw, and then we also saw like how to basically solve the Bessel function, and so on and so forth. Then we went from the 1D transient flows to 2D steady flows. Okay, for instance, we looked into the flows between rectangular channels. Okay, flows between equilateral ducts. Okay, and we also saw something like whenever there's a flow between a rotating porous cylinder, when the cylinder was itself rotating and it is porous, which ended up for us getting two directions of velocity, and this means that our problem was inherently a two-dimensional problem in nature. Okay, after like this, so after solving the Navier-Stokes equation, we went on to something which is known as the lubrication theory, or the creeping flow analysis, where the creeping flow is essentially a part of lubrication theory. Okay, where we saw that in creeping flows, okay, when we invoke the assumption that when the Reynolds number goes to 0, we end up getting a balance between the pressure gradient and the viscous forces. And then if we are interested in solving 2D axisymmetric problems, we get a biharmonic equation of the stream function. Okay, and this is something that we have shown, that we have studied extensively. And then as a prototypical example, we looked into the motion of a simple sphere in a background parabolic flow. And if the sphere is now free to set in motion, what would be the steady state velocity of the sphere whenever there is a background parabolic flow or a background Poisson flow in the limit of creeping flows analysis. Okay, so once we are done with these things, then we moved into something which is known as the boundary layer theory, which is very much important to you, both in the context of the course and also in the context of your exam. You need to be very much clear with the boundary layer analysis. Okay, the scalings that we do in the boundary layer analysis, the Blasius solution, and more importantly, the momentum integral equation. The momentum integral approach is so by using couple of examples, we indeed saw that the momentum integral approach is indeed very powerful, and the velocity profiles that we took, if it satisfies the boundary condition. Okay, for instance, if we use the third order velocity profile, we use the sinusoidal velocity profile, and we saw that the boundary layer thickness delta as a function of x, that variation closely resembles to that of Blasius's solution. Okay, then we looked into something which is known as the Faulkner scan solution, which is basically based on the fact that when you're u infinity, the first stream velocity in boundary layer theory becomes a function of x, which means now we are prone to all those boundary layer separation and all those things. And finally, we ended boundary layer by discussing on boundary layer separation and how does the presence of an inflection point, is the sufficient condition for boundary layer separation to take place. So once we are done with boundary layer, we started a very important topic which is known as the hydrodynamic stability, and then we ended up studying which is known as the linear stability analysis, which means that the perturbations or the magnitude of the perturbations are very less compared to the base flow. And once we know that we are in the limit of linear stability analysis, we saw systematically how do we solve a linear stability problem. For instance, we derived we performed the stability analysis of a parallel invisible flow, and we derive an infamous equation which is known as the Rayleigh stability equation. In the last session in this class, before like coming to this class, we also saw some criteria, where the Rayleigh stability equation holds good. For instance, we looked into three criteria. One, the Rayleigh inflection point criteria, which says that if there is an inflection point, this is a necessary condition for instabilities. However, that's not a sufficient condition, and a stronger criteria for that says that which is known as the Jortov's criteria, which is a stronger criteria to the Rayleigh stability the Rayleigh inflection point criteria. And then we also applied these two criteria in looking into the fact that Couette flows are essentially stable flows. This means that if you add a disturbance into a Couette flow, your disturbance will basically decay with time in the limit of linear stability analysis. We ended by discussing one more criteria, which is known as the Howard semicircle criteria. This is something that we discussed in the last class. You can go back to your notes and just see. And the Howard semicircle criteria says that for instabilities to occur, we know that Ci, that is the imaginary part of the eigenvalue, should be greater than 0, and it must lie within a semicircle whose radius is half of Cmax minus Umax minus Umin, and its center is half of Umax plus Umin, where Umax and Umin is the maximum and the minimum values of your base profile. We ended this interactive session by learning something which is not directly, so it may not come into your exam how to solve an eigenvalue problem, but this will definitely give you an idea when you go into further courses, like if you take courses like CFD or if you take more advanced courses on fluid mechanics, it will definitely give you an idea how essentially do we solve an eigenvalue problem. Because the equations for hydrodynamic stability that we end up, for instance, the Rayleigh stability equation, the Orr-Sommerfeld equation, these are just eigenvalue problems. So how do we solve eigenvalue problem both analytically and numerically, and using finite difference method to discretize the governing equation is something that we saw in this session. So with this, I would end the session here, and I would thank everyone for joining this course at any interval of time that you just join. And I would be very I'm very delighted that I would be very delighted if I am able to just put in some amount of effort for you so that you have understood this course in a better way. Thank you for joining NPTEL, and yeah, thank you all. So if you have any questions, you can ask, or else I will just close this meeting. Okay. Okay. Thank you. Yeah. Thank you for joining. Okay. If you don't have any questions, thank you for joining. Thank you for joining the sessions. Thank you for
One
choosing.
doubt.
Yeah. Yeah. Just, yeah. Tell.
Can you hear me?
Yeah. 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 Go on.
Yeah, I already had mentioned about one question.
Yeah.
That is related to assignment.
So it's related to assignment.
Just a
Can you tell me?
second. Just a second.
Yeah. Just take your time. Is it that boundary layer thing that you are telling? So that boundary layer thing, I know the question is wrong, but I have communicated that. So is that the thing?
Five.
Okay,
It's
assignment
related to
five,
week
right?
five.
Okay, assignment
Yes,
five. What's the question?
assignment five.
Yeah.
Uh, question, num- question number two.
Okay, okay. That I think you asked it in the discussion group, right? Did you ask this question in the group?
Yeah, but they told that it's shown in lecture video like the coordinates by z comma y.
Okay.
But
Okay, I
actually
see. I
we are
remember. Okay,
representing
okay.
these
Okay.
coordinates.
Yeah, I understood. Okay.
Actually we are representing coordinates x comma y comma z.
Yeah, yeah, yeah. Actually, I understand that question was little bit like it should have been formed in a much better way that I understand. But anyway, I'll do one thing. I'll try to directly contact with. See, the professor of this course is from a different IIT than the IIT than here. Okay, so I'll try to like connect with this for this
Okay.
question. Okay. Uh, you don't need to worry of this question at this point of time. Okay, if it is wrong, if the professor feels it's wrong, okay, I will surely like I can assure you that if the question is wrong, okay, then you will surely like
Yes.
get
It should be like
yeah.
yeah, it should be like x comma y comma z
Okay.
or y comma z at least. But it
Okay,
is
okay.
given
Yeah,
like
I
z
remember.
comma
I
y
remember the
comma.
questions. Yeah, that I saw it when I think you told me this thing some weeks back also. I remember that. Anyway, I'll try to communicate this. I'll try to communicate it to the best of the ability that I have. Okay, and then I'll try to like mend this. Okay. I'll surely like try
Okay,
to
okay.
like reach for this question. Okay. And I'll also see this is something that I can't
Oh,
tell how many number of questions it would be, but I can ask about this and about this in to the like authority whosoever is like doing whosoever is making the questions and making the exam paper for this. Okay, I think this will do.
okay, okay.
Okay, all right. So if you don't have any other
Mm,
questions,
mostly the
yeah,
questions
yeah, go on. I
mostly the
think
questions will be similar to the assignment, right?
yeah, yeah, yeah. It's similar. See, in the assignments are very thoroughly like prepared and it's very see they prepare assignment after each and every topic, which means once you do your assignment like sincerely, this means that I don't think you should be in a position of like really worrying of how the questions in the exams would be because the assignments are very like it's not that they are just giving one assignment after 5 6 sessions. It's not like that. They are in fact giving you assignments after each and every session, which means that the assignment questions are really very rigorous. And if you can do that, I don't think so you will be in a position of really worrying about the exam. Okay, so it should be similar to the ones that since this is a computer based exam, okay, and it's not a written exam, as I'm aware, it's a computer based exam, right? If I'm not wrong.
Yes, yes, computer
Yes.
based.
So this means that your questions would be similar to that of the assignments only. Okay. All
Okay,
right.
okay.
All
Thank you.
right. Then further, if you have any queries, always post it in the discussion forum. Then either one of the TAs of this course will always reach back to you. Okay. And I will try to like try to coordinate with them for these two queries basically. Okay. All right then. Thank you very much. I'm calling this meeting off. Thank you for joining the course Viscous Fluid Flow. Happy learning. We hope you continue with NPTL for the years to come. Okay. Thank you very much.
Okay, thank you.